What is going on, guys? Welcome back. In this video today we're going to learn how to improve model performance in PyTorch by using data augmentation, which is the process of generating new data from existing data. So let us get right into it. Alright, so the basic idea behind data augmentation is to improve the model's performance by showing more data to the model, and this data is generated from existing data. So we don't add new images to an image data set, but we create new images, we generate new images based on the existing ones. For example, this can be done with very simple transforms, horizontal or vertical flip, rotations, cropping, increasing or decreasing the brightness, contrast, saturation, and so on, just to create more data that we can train the model on. Now, the reason this can make the model perform better is because it learns to generalize better. It makes it more robust because it can show the same image of a dog, for example. If we have a dog or a cat classifier, we can show an image of a dog and we can show the same image slightly rotated or slightly moved, or maybe with more brightness or with less contrast or with more saturation and so on. So we just have artificially created more training examples that we can use to make the model perform better. And this is what we're going to explore in this video today. I already have the model, the training logic, and the evaluation model implemented here because this should not be a video on how to build simple neural networks in PyTorch. But I'm going to briefly go through the code so you know what we're doing here. We have a simple convolutional neural network. Basic idea is 2 convolutional layers followed by 2 fully connected layers, and in between we also have pooling layers. So basically we get the input, we apply the first convolutional layer, a ReLU activation function, a pooling layer, the same thing for the second convolutional layer, then we reshape the data, we apply the first fully connected layer, we apply ReLU, we have a dropout with a 50% probability, and we have a fully connected layer 2 here, and that's basically our neural network. Now the training loop is basic training loop that you have in PyTorch. This function takes as a parameter the model, the train loader, the criterion, optimizer, and device. Device is going to be the GPU, model is going to be our CNN. The train loader is what we're going to define here in a second. This is going to be the part where we add data augmentation. The criterion is just going to be cross entropy loss, and the optimizer is just going to be atom. We're going to pass all of this to the function, and the training loop is quite simple. We set the model to training mode, we have a running loss, we go through the images, we send them to the device, we apply the zero grad, we call zero grad, we get the prediction from the model, we calculate the loss, we backpropagate it, we optimize, and we add to the running loss. That's basically it, and in the end we return the loss for the epoch. For the evaluation, we put the model in evaluation mode. We have correct equal to 0, total equal to 0. Then we say no gradients have to be computed because we're not training. And then we go through all the images, make predictions, and if it's correct, we just add the number of correct predictions to total. And we always add the number of all the samples to correct, and then we get the accuracy by returning 100 times this ratio. So that's quite simple, very basic stuff. And what we're going to do now is we're going to train this model on the Cypher10 dataset, and we're going to do it one time without data augmentation and one time with data augmentation, and we're going to look at the difference in accuracy. Now, of course, this is going to take longer to train because the more data we have, the longer the model has to train. So by introducing augmented examples, we of course have more training time. So you're not getting more accuracy for the same runtime, but you don't have to get more data. You don't have to seek out more images. You don't have to download or scrape images. You can just use the images that you already have to improve the performance of the model. So we're going to define a function here, load data, which is going to take a parameter data augmentation. And this is going to be false by default. And what we're going to do in this function is we're just going to return the train and test loader for the data. So we're going to have transforms, a simple transform pipeline, transforms original, and this is going to be transforms dot compose, and we're going to define a very basic transformation here, transforms to tensor, and then we're going to normalize. We're going to say transforms normalize, and we're going to pass for each channel the mean and the standard deviation. So we're going to say 0.5, 0.5, 0.5, 3 channels since we have RGB, and for the standard deviation as well. So that's the basic non-data augmented transform pipeline. And we're going to do now another one, which we're going to call transforms augmented. And this is going to also be transforms compose. But here we're going to do a bunch of things in addition to that. And of course, if we don't do data augmentation, we're just going to use this transform. If we do data augmentation, we're going to use this transform. And then we're also going to use this transform separately. We're going to have 2 data sets, the original and the augmented, and we're going to combine them together. So we're going to have twice the data because we're using the original samples and the randomly augmented samples. So what we're going to do here first is we're going to start with a random horizontal flip. Then we're going to do a random rotation, 10 degrees to the left or the right. If you just provide a single number, it goes both ways. So it goes from -10 to 10, or actually it's like a range. I think you can also have stuff in between. Then we do transforms dot random crop. Size is going to be 32, padding is going to be 4. You can play around with these, of course. And then we're going to do the same thing as above. So we're going to copy that, and we're going to paste it down here. And that is going to be our augmented transform pipeline. So all we need to do now is we need to apply these to the Cypher10 dataset, and we need to return the train and test loader. So we're going to say, if we have data augmentation enabled, what we're going to do is we're going to say, the original data set is going to be equal to data sets. By the way, I do have some imports up here if you didn't see them. So from Torch Vision, import data sets and transforms, and also from Torch Utils data loader. These are, of course, important. You need to use them. And, of course, install Torch and Torch Vision if you don't have them on your system. But since this is kind of a more intermediate to advanced tutorial, I assume you know what PyTorch is and how it works. So original dataset is going to be equal to datasets.cypher10. We're going to specify that our root directory is going to be current/data. We're going to say that we want to have the train data. We're only going to apply, obviously, the augmentation to the train data. There's no value in augmenting the test data because it's only used for evaluation. The only reason to augment is to have more data to make the model generalize better. So we're going to only do that for the train data. Then we're going to say download true because we want to download to the disk. And we are going to say transform for the original one is going to be just a basic transform original pipeline. Now we're going to copy that and do the same thing for the augmented dataset. So augmented dataset is going to be equal to dataset, Cypher10 data, everything the same. Just here we're going to say transforms augmented. And then in order to have the complete dataset, we're going to say train dataset is equal to actually torch utils data dot concat dataset, and we're going to concatenate these 2 datasets into a single one. So we're going to say original dataset and augmented dataset are going to be combined into train dataset. And of course, if we don't have augmentation on, then we're going to just take the original dataset and name it train dataset. So basically the case for, or the case without data augmentation is going to be just this, but we're going to call it this because we want to use train dataset no matter what we do here. All right, so with that, we're also going to define the test dataset. Actually, for this, we can copy and paste this one and just replace train by test and set train to false. Everything else stays the same. And then we can define the 2 loaders. So we're going to say train loader is equal to data loader based on the train data set. Batch size is going to be equal to 64, and shuffle is going to be true for the train data. And then we're going to define number of workers. Now, if you want to load the training data faster, you can define to use multiple workers, or you can specify that you want to use multiple workers. What I usually do is I import multiprocessing, depending on what machine I'm on. multiprocessing, and then I run multiprocessing.cpu count. And in this case, I have 16, so I will do usually half of that, so 8. And this should not crash my system and just increase the speed. So I'm going to say number of workers 8. Then I'm going to do the same thing for the test data. And I'm going to say test data set. Shuffle is going to be false for this one. Still 8 workers. And then we're going to return train loader and test loader. And of course, I have a problem. What's that? I didn't close this. But that's not it. Or actually it is that, but I need to do it here as well. There you go, seems to work. And now we're going to compare the two approaches. So we're going to train the full model and evaluate the model on the data without augmentation, and one time we're going to do it with augmentation. So we're going to say that we want to define the device to be equal to torch dot, I think it's torch dot device, and it's going to be CUDA if torch.CUDA, I think it's called is available, else CPU, and we're going to train for 25 epochs. So I'm going to have to cut this because this is going to take some time, but we're going to define the model, we're going to load the data. So let's say train loader, test loader is equal to the function that we just defined, load data. And we're going to set data augmentation to false explicitly here so that we know what we're doing. The model is going to be the simple CNN, and we're going to send it to the device, so to the GPU in my case. The criterion is going to be equal to NN cross entropy loss, and the optimizer is going to be equal to optim atom. On all of the model parameters. So model.parameters, and we're going to set a learning rate of 0.001. That should be fine. And then we're going to print without augmentation, and we're going to just train the model. So we're going to say for epoch in range epochs. We're going to say the loss of the current epoch is equal to train model. And we're going to pass all of these things now. Model, train loader, criterion, optimizer, and device. So these were the things that we defined up here in the signature. Model, train loader, criterion, optimizer, device. And we're going to get the loss by doing that. So we're going to print for each epoch a formatted string, which is going to say epoch, and then we're going to say loss is equal to, and then loss, like this. And in the end, what we want to do is we want to evaluate the model. So we're going to say the accuracy is going to be equal to evaluate model, model, test loader, and device. And then we want to print the accuracy in percent. So let's do it like this. That should work. Maybe let's say accuracy. And that is it. Now we're going to copy all of this and we're going to paste it down here. And we're going to change this to true. And we're going to say with augmentation. Everything else stays the same. And we're going to see how well this goes. Now, just to make sure I didn't make any mistakes here syntactically, I'm just going to run this on 2 epochs to see if it works. And then I'm going to do it on 25 epochs if this works without any exceptions. So now it downloads the data, and then it should start with the training process without augmentation, epoch 0, epoch 1, 64.89%. With augmentation, 0, 1, 66%. Okay, so already we are seeing the effect, but let's go and do it properly for 25 epochs and then evaluate this afterwards. All right, so the training and evaluation is done, and we can see when we scroll down for the non-augmented approach, we have 72.81% after 25 epochs, and when we scroll down here with augmentation, we get 77.51%. And this is just by reusing images already in the dataset and applying some very basic flipping, rotating, cropping, and you can add more stuff. You can also do one transform for flipping, one transform for rotation, one for cropping, and then you can have 4 data sets that you merge together if you have enough time, and that's not really a problem. Maybe data is more difficult to get to rather than hardware and runtime. So that is a very powerful approach, and it doesn't only work with images. This is an image example, but you can use the same thing with user sessions and recommender systems. You can use the same thing with text. So just a quick example here. I'm gonna open up a new markdown cell to show you that if you have some click behavior of users, let's say you have user clicks items 1, 2, 3, 4, 5, and in the end he buys item, I don't know, 8 or something. Just now a random example. One augmentation would be to, reorder them. Maybe the order is not as important. So maybe you want to say, okay, make 3, 2, 1, 4, 5, or anything else like shift the order, or maybe if you have next item prediction, you can change what's visible. Maybe you can mask certain items here to make it more difficult. This is now just me giving some random examples, but data augmentation in general, taking data that you already have, transforming it in some way, and then using it in addition to the original data can oftentimes lead to better performing models, and you don't really need to do anything other than some basic transforms. So that's it for today's video. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.